So in this video, I just want to talk a little bit about the zeros of polynomials and long division and how all of it is interconnected. So in this problem, we have one real zero of the polynomial function is x minus 1, and they want us to find the rest of the zeros. So we know that x is equal to negative 1. What we could do here is I'm going to work backwards a little bit. So I just got the right side to equal 0. So what I'm looking at here is a factor of the polynomial that's given to us. Okay, you can kind of think of this as the zero product property in reverse, right? So we have 1 0. Well, there's got to be two other zeros because this polynomial has a degree of 3. So we know that there are going to be 3 zeros. Whether or not they're going to be real or imaginary, we don't know, but we know there's going to be 3 zeros. So if we had all the zeros, we'd have 3 solutions, and generally speaking, we would have gotten those by using the zero product property. And we would have set all the factors equal to 0 if it was factorable. And the step before that, we would have had our polynomial all factored, and it would have equaled 0. And the step before that, the step before that would be the function that's given above. We know that it would look exactly like this, right? So pretend we're working from bottom to top, right? So if we're starting here, if we were able to factor it, and then we're able to use a zero product property, then we would have gotten to this point, and we would have gotten one of our zeros to be negative 1. The problem is we don't know any of these other factors, which means we don't know these zeros. So how can we find them? Well, factoring a polynomial that has a degree 3, that's not a perfect cube, or I should say a sum of cubes or a difference of cubes, is pretty difficult. So what we're going to do instead is we're going to divide by the factor that we know, which is x plus 1. And we're going to divide this polynomial by x plus 1. And the result is going to be some quadratic factor. Okay, it's going to be a quadratic polynomial. So let's go ahead and let's do the division. So we got this to be x squared, and we're just going to multiply it. Okay, multiply it around. This is going to become plus x squared. We're going to subtract these. We get x squared. We're going to bring down the negative 5x. Okay, so what times x gives us x squared? So it must be positive x. That should be x. There we go. We're going to subtract that. So just to be clear, I'm kind of doing this here as we go. So now we subtract it. Those cancel out. Negative 5x minus x, that gives us negative 6x. Bring down the negative 6. And now we're going to just continue that process. We're almost done here. So what times x gives us negative 6x? So this has got to be negative 6. And then we're going to multiply negative 6x minus 6. They're exactly the same. So when we subtract them, we're going to get no remainders. So this is kind of nice. So what this means now is this polynomial, okay, that dividend, can be factored as x plus 1 times x squared plus x minus 6. So now, what we're going to have to do is try to factor that. Hopefully, we could factor it. I know we could factor it. So we could set up, so this first x plus 1 is just what we divided by, getting carried down. Okay, so now x squared plus x minus 6 can be factored as x times x, it's going to be plus 3 minus 2. And we could distribute that to double check that. So this is our polynomial now in factored form. Okay, so on the graph, we have 3 zeros. We have 1 at -1. So if our factor is x plus 1, if we use the zero product property, right, going back up above, let's actually fill this in, okay? So now let's go up here. Let's do it in a different color here so it stands out a little bit. So we have the x plus 1, that was the one given to us. So this one is x plus 3, and this one is x minus 2. So if we use the zero product property, okay, either x plus 1 is equal to 0, x plus 3 is equal to 0, or x minus 2 is equal to 0. We solve this for x. So x is equal to -3. The one on the right, we solve for x. So x is equal to +2. So we have zeros at -1, -3, and 2. That means x-intercepts at -3, -1, and 2. So now we can imagine what our polynomial looks like, right? Our polynomial is going to do one of these. It's either going to go like this, or it's going to start up here and look like that. So how do we know which way it goes? Well, if we look at the original equation, we can see that the largest exponent is 3, so it has degree 3. So the degree is odd. So if you think of its parent function is x cubed, which looks like that. So it starts down in quadrant 3 and ends up going up in quadrant 1. And that first term is positive, so this is not reflected over the x-axis. So we know it's going to have that general shape. So it is going to start down here, and it has that general shape. And now, does it look exactly like this? You know, we don't really know, but we could go to Desmos. We love Desmos. At least I love Desmos. And let's check it out. So we have x plus 3, x plus 1, and x minus 2. So notice I could enter this in factored form in Desmos. Sort of helps me remember it. And you can see there's a general shape that I drew. There are our x-intercepts, and that from Desmos we can find a couple of other things. We could find this relative maximum right there. It's a little ugly, 4.061. We have our y-intercept. That one's nice and pretty, 0, -6. And then we have another relative minimum at 0.786, -8.209. So what I generally do here, I'll put my y-intercept there, because we could actually find the y-intercept really easily if we just plugged 0 into our function, which, why don't we do that right now? It's good practice. So we could plug 0 into our function, and I could plug it right into factored form. So I'm plugging 0 in for x everywhere I see an x. So this becomes 1 times 3 times -2, which is that -6 that we have right there. Okay, so there's the connection between long division and the polynomials that we've been looking at in the last couple of sections. And there's a lot more to polynomials. If we had more time, we could spend looking deeper into these polynomials. But I think for the time being, we have a good enough foundation where we're at.